Hey guys, this is Srini here, and you're watching Python tutorial videos on my channel, Python for Microscopists on YouTube. In today's tutorial, we're gonna learn a little bit about histogram-based segmentation. This is where you take gray level ranges and then segment different regions that's got different gray levels. So of course this technique is going to work only if you can identify or distinguish different regions based on histogram only, based on gray level only. uh, if you have different regions, let's say with different texture, but the gray level is pretty much the mean gray level the same, then there is no way you can do this. In fact, you have to use some sort of a pre-processing, some texture-based region identification, maybe entropy filter, or some of those filters to separate the regions before you can do histogram-based segmentation. Sometimes you may even have to use machine learning to segment your images. But most images, with a little bit of pre-processing, you can actually use histogram-based segmentation to separate them, especially the images from scanning electron microscope, for example. So this is why I've actually downloaded a backscattered electron image from Google search, and that's what we're going to use to demonstrate the histogram segmentation today. So let's jump in. The IDE that I'm going to use is Spider IDE. That's part of Anaconda distribution. And again, this is because it comes with most libraries prepackaged. And the image I'm going to use, in fact, this is the one I downloaded from my Google search, and I've added a little bit of artificial noise to this, so it makes it a little bit of challenging. And I would also like to extend my previous tutorials discussion about denoising by actually using it here and then adding segmentation as the next step. So I have the page open for scikit-image non-local means denoising. So while I have this open, let me go ahead and copy and paste the appropriate libraries and functions that I need to actually perform the non-local means denoising. First of all, this is the line that actually performs the denoising. So let me go ahead and start with that. Okay. And denoise NL means, where is it? That is part of my scikit-image restoration. So let me go ahead and copy. And I'm also copying estimate sigma because that seems to be part of my, one of the input parameters that I need to get by using this function. So let me go ahead and copy this, and also copy this line where we estimate sigma. Okay. And while we are actually, sorry, let me bring this down. While we are copying stuff, let's go ahead and copy this another line that converts images to float, because non-local means actually works on floating images. Otherwise, you're doing all the math, and then it doesn't make sense if you work with an integer numbers, in this case. So let me go ahead and import. We don't need data because we are going to use our own images, and import image as float. I'm also going to import image as ubyte because after everything is done, I want to convert our images back to 8-bit, and we can open it on our computers. We can actually look at it. And also the range of 8-bit images goes from 0 to 255. So when we plot it on a histogram, the ranges make sense. 255 looks white, 0 looks black, so it matches with our expectation of what an image range should look like in a histogram. So let's jump in. And one other thing, we are missing np, which is numpy. So let's go ahead and add import numpy as np. And we also would like to plot this. So from matplotlib import pyplot as plt. We have done this so many times now, we know why. Like we know a few libraries that we would like to import right from the beginning. So step one, let's go ahead and read our images. So image equals, I would like to read it as float. So image as float io.imread, and our image is in images slash, and what is it called? BSC Google Noisy. So BSE underscore Google noisy.jpg, and this is the image we're going to use. Now, step one, like I mentioned, let's go ahead and denoise this image and then look at the histogram. Otherwise, it doesn't make sense to look at histogram right from the beginning. I used IO and it's saying undefined name. That's because I haven't imported IO. Let's go ahead and add IO to our SK image. That should be fine. And our image name is not noisy. It's called IMG. Same thing right here. Our image name is IMG. And the patch KW, the 2 stars right before the patch KW means we are unpacking a dictionary called patch underscore KW. And we haven't created that dictionary. Here, I think they did that. Yeah, they're, this example actually, I don't know why, but they have defined this patch size, patch distance, and multi-channel equals to true as a dictionary, and then unpacking here. Let's go ahead and unpack it, define it directly. Patch size 5 and patch distance equals 3 and multi-channel equals true. Okay, so once we have that, now we just need to look at the image. I believe we have pretty much everything we need except imshow denoise, and let's go ahead and map it in gray so the image looks familiar. So plot, run this. Okay, so looks like we made a mistake here, which is multi-channel equals to true. Again, I at least make one mistake per video. So this is my first one, and let's go ahead and show the image. And we need to see any second now. And once we have the image, let's go ahead and look at the histogram and then pick the ranges for our histogram based segmentation. And plt.imshow. Okay. So we do have our image here, but one thing I forgot to do is if you look at this, our denoise image is float 64. Maybe we can just convert our image right away so we don't have to do it. The next step is looking at the histogram and segmenting it. So let's go ahead and convert this image. And again, I'm going to call this denoise underscore 8 or ubyte. Let's just go ahead and call this ubyte equals image as ubyte. Okay, and which image denoise. Okay, so this actually converts our image back to ubyte, and let's run this one more time just to double check that our image is indeed an 8-bit image with 0 to 255 range. And the next step, like I mentioned, is to have having a look at histogram for this, and then just defining the ranges for each segment. So the reason why it's probably taking this long, I was wondering, well, what's going on with my computer, is the fast mode equals false. Let's convert that, let's change that to true and see what happens. Okay, so I just changed it to true, and hopefully it should be faster now. And the quality of image, yeah, it's so much faster. You know, it's almost instantaneous. So this is why, and the quality of image, the difference in the quality of image, I don't see it much. So I'm going to just change the fast mode to true. Sorry about the delay over there. That was literally 2 minutes that we lost, but at least we learned something there. So anyway, we have our denoised image. Now let's go ahead and look at the histogram. And by the way, the denoised image ubyte is 8-bit. So we're all set. Okay. So which means our histogram goes from 0 to 255. So when I'm going to do plt dot hist, which is nothing but our histogram, I can just do denoise noise underscore ubyte, and this is the image we are going to look at, but then dot flat. And dot flat actually flattens the 2D array into one dimension, because for my histogram I just need like a just one-dimensional list of numbers. Yeah, so that's what dot flat actually does here. And once we have this, we can define how many bins this is again, I believe, optional. And we can also define the range equals to, let's go from 0 to 255. And let's go ahead and plot this. So we should see an image, and we should see, well, we should see a histogram. Okay, that's not bad. One peak, two, these two peaks are very close, 3 and 4. So let me actually, this goes from 0 to, so let me actually change this range to, I don't know, let's say 75, or let's do 80. So we can just zoom into this region and identify the value for that valley over there. So we can use that. So that's nothing but, let's say 55 is where the separation is happening. So let's go ahead and define our different segments. We are getting very close to segmentation. Segment 1 equals, well, we have to define our denoise underscore u byte, okay, and less than or equal to a value of 55. Okay, so my segment 1 is nothing but, it's a binary image where all the pixels are extracted from the denoise u byte image, and all of these pixels are coming from a gray level less than 55. So this is nothing but this one. If we really want to be nitpicky, we could have separated this into our fifth segment, but let's just, for now, let's not do that. Our segment 2 is equal to denoise u byte, and this time it's greater than 55. Okay, and denoise u byte less than or equal to, let's actually do about 110 over there. Okay, 110. So what this line does is, again, we are picking all the pixels between 55 or 56 and 100. And I'm going to do exactly the same for segment 3, except our range here is greater than 100. Actually, let's do 110. I thought we said 110. Let's do 110 here, and less than maybe 210. Okay, and less than or equal to 210. And finally, let's just do one more. Segment 4, or segment 4 is greater than or equal to 200 and, well, just greater than, we don't need equal. This is 210. This is going to generate 4 different images, each a binary image. Okay, so this is it. This is segmentation. So now we have segmented this image. I can go ahead and display these images. But then let's show all of these images into one image in different colors. Otherwise, it's not fun. Okay, so how do we do that? I'm going to create, sorry, I'm trying to find my mouse here. Okay, I'm going to create something called all segments. Okay, and this is filled with, let's just do zeros. It's filled with zeros. And then denoise our image is u byte. Okay, and dot shape of the same shape, fill it with all zeros. Okay, and let's so all I'm trying to define is an image, and then I'm going to fill that image with relevant information, with different segments. So let's just do denoise u byte and dot shape, and let's do 0, 1, and then the 3 corresponds to the 3 red, green, and blue channels. And so this is nothing but denoise, create a blank image that is same size or array shape as of our denoise u byte image. So create a blank image that's the same size as the image that we want, the target image. Okay, so that's exactly what I did. Filled that with all zeros, and now let's actually fill one by one. So I want to call our segment 1 in, I'm actually thinking as we do, let's do red, green, and blue, and segment 4 as yellow. I was thinking only 3 colors, why not just add another color. So all segments, this is what we created with all zeros, and segment 1, okay? And I want my segment 1 pixels all colored in 1, 0, 0. Okay, and let me copy and paste this so we can do it a few times. And this, and this, and segment 2, let's color this green, so red, green, and segment 3, let's do blue. Okay, and finally let's do 1, 1, 0, which is red plus green. It should be in yellow. Okay, let's do this segment 4. So that's pretty much it. Plot.imshow, and hopefully we should see a nice image showing us all the segmentation. There you go, and these streaks means I'm plotting something else and I forgot to do that. And let's do this one more time. Sorry about that. And we should see a nice image. There you go. This is a nice, well, kind of nice image. And we do see some of these yellow pixels on the grain boundaries, or maybe they're green. We do see some red pixels scattered around here. So this is, again, we don't have like a perfectly clean image. So we are going to have that. And there are various ways of cleaning it up. I mean, there are filters called you can do like opening and closing operations. Again, if you're like an ImageJ user, you probably know what I'm talking about. So you can clean the image up. And okay, so far it's only 17 minutes in this video, so let's take 3 to 4 minutes to actually do that. So I believe these are part of SciPy. Let's import nd image as nd. Again, nd image has some nice tools. So segment 1, let's say cleaned. Let's do a binary opening and a binary closing operation. Okay, so the binary opening, I always get this other way around, but anyway, binary opening, I believe, takes care of stray pixels, and binary closing takes care of stray voids, wherever you have like one pixel surrounded by a bunch of other pixels and that one pixel is blank, it fills it. So it's nothing but cleaning up stray pixels, whether they are dark or bright pixels, yeah? Because these are all binary images. We either have 0 or 1. So that kind of helps us a little bit. nd dot, and this is binary closing, there is binary opening. Let's start with opening and then take that image and do closing. Okay, so binary opening, and what do we want? Segment 1 image. And the kernel that we want to use is np.once, for example. Let's do 3 and 3. Okay, so a 3 by 3 shape. And I'm not going to worry about other parameters there. And I'm going to do pretty much the same thing, segment 1. In fact, let's call this open so it makes sense. And closed equals nd dot binary closing. And again, same thing, segment 1, np dot once, 3 by 3. I believe this should clean the image. And what is this saying? Unexpected indent. Okay, sorry about this. And let me copy these two and then do exactly the same. I could have put this in loop because we have 4 things, but for now, let's just do it the easy way. And I'm gonna do this segment 3, segment 3, segment 4, 4, and here this is 2, 2, and by the way, which image? Here, actually, let's take segment 1 opened, right? I mean, we are opening it, and then let's take that image and do the closing operation. I think that is a better way. I mean, that is the best way. And let's, okay, and this would be, again, same exercise, 2, 2, 3, 3, and I do not like that, so let's change it, and let's change this to 2, 2, 3, 3, 4, 4, and let's also do this here, segment 1, 4. We have done so many things, and I hope we followed the procedure. We'll find out, you know, if something is wrong. So I'm gonna take that image off, and then take that line off, and then all segments. And now let's I'm actually thinking about yeah, we should create this again. We should do this one more time, sorry. And once this is done, let's actually create all segments. Let's call this cleaned. Okay, np zeros, denoise, ubyte, shape 0, denoise, ubyte, shape 1 and 3. This is, again, that line is creating a blank image with all zeros. We already talked about it. And now all segments underscore cleaned. Yeah, we are going to print that. And now we need to copy all of these so we can add these colors to the cleaned image. And instead of segment 1, what is the second operation? We did segment closed. Segment 1 closed, segment 2 closed, segment 3 closed, and segment 4 closed. So let's go through this one more time just to be sure. So here we created this, and until this point it worked very well. So let's not worry about it. So I did the opening operation, segment 1, closing operation of segment 1, 2, 3, and 4. I did exactly the same for all of these, and 1, 2, 3, 4. And then we created a blank image of exactly the same size as denoise ubyte shape. So that's good. And to the cleaned image, we are adding, see, sanity check is always good. We are not adding that to cleaned image, so let's change that. And here, okay, so to this blank cleaned image, we are actually assigning a red color to all the pixels corresponding to segment 1 closed, which is the second image there. Okay, now I think we are all set. Let's go ahead and run this, and hopefully we should see a segmented image that is very clean. If so, we can go ahead and save that image. So that is much better compared to the image above, as you can see. There are still some pixels here and there, but that's okay. So let's go ahead and save, and let's call this images segmented.jpg, and let's run this, and we should see an image right here, and let's place it right next to our original image and compare this. We can go back to all the way zooming out, and there it is. Original image, segmented image. In fact, that's not a bad job. You know, even on the grain boundaries, I don't see any pixels hanging out, you know, any green pixels, and that's where the ambiguity usually is, you know, when we are segmenting images. But it looks very clean. I mean, this region could have been better, so you can actually play with the histogram values, or maybe use some different filter. But this is actually not a bad way of doing your segmentation, especially if you have backscattered electron images. Anyway, I hope you found this video to be useful, and let's cover a different topic in the next tutorial. Thank you very much.